Thank you, Dr. Sumi, and good afternoon to everyone. Today is a topic that tends to generate a lot of excitement, seismic attributes. And I have about 30 or 35 minutes to kind of give you a quick overview. There are courses that are given within industry that run 5 days or more on seismic attributes. So I certainly am not going to be able to cover every aspect and talk about every application. The images on the first slide here is for a study that I'll talk about as the lecture proceeds, but you can see this is a predicted porosity map, and so the colors here represent 0 up to 18% porosity, and I'll go into more details as we proceed. This is the slide I have included for many of the lectures, just reminding the terms of use and that the materials are intended for students and for professors, instructors, adjuncts, even teaching assistants that would help teach the students. It's also available for students to do on their own pace as a self-study. So a good place to start is with a definition of what seismic attributes are, and this is my definition. So seismic attributes are mathematical descriptions of the shape or other characteristics of a seismic trace over a specified time interval, or if we have our seismic converted to depth, over a specific depth interval. And so I'll expand on that as we proceed. In terms of using attributes for stratigraphic analysis, we can use attributes to help us understand things such as the types of environments of deposition. In some cases, the presence of hydrocarbons gives us anomalous attribute responses. We may see an anomalous amplitude that's associated with the presence of gas or presence of oil. Typically, we use 3 types of attributes, and I'll be talking about these as we proceed: horizon local attributes, interval attributes, and surface attributes. And here again is my predicted porosity map as an example. In this case, 4 different attributes were combined in an equation so that I could take those 4 attribute values at each trace location, each XY, use that equation to predict what the porosity would be, anticipated to be, and then use a color palette to emphasize that the really high porosities are in the hot colors. This is a different type of attribute. This is a frequency. This is for 16 hertz within the spectrum. This is a time slice from a 3D cube off of Louisiana. And at 16 hertz, bodies of certain thicknesses light up, so to speak. Thinner ones would not be as bright, and thicker ones would not be as bright. And this example, and you can see the internet reference down here, it shows the distributive system for fluvial systems, and I think it's quite easy to understand that these white sinuous patterns here are marking major fluvial channels. So horizon attributes, those are attributes that are measured relative to an interpreted horizon, such as the green horizon here. The most common attribute, and sometimes people overlook this, is the two-way time to the green horizon, or if it's a depth cube instead of a two-way time cube, the depth. So some people think the most common attribute is amplitude. I would say that's the second most common. Two-way time or depth, I would say, is the most valuable, most often used attribute. We can look at the maximum dip at a particular location for the green horizon. We can look at what the azimuth of that maximum dip is. We can look at the reflection amplitude along that particular red. Red would be a trough. If I have the polarity set the way I usually do, we could look at the curvature that's on that interpreted horizon. So horizon attributes usually measure some property of the peak or the trough, in this case the red half cycle, that the horizon has been mapped in. Here's an example. This is a map view. It's the attribute horizon dip. The dips that are gentle would be in the lighter to yellow to orange, and the dips that are steeper are in the purples and the blacks. And so you can see a lineation here of high dip, and the units on this would be X number of milliseconds per trace spacing unit. So this happens to be a fault. There's another fault that cuts through here. And then there's kind of spaghetti on my plate here. Those are stratigraphic features. And a quick way to determine if something you see on a horizon dip map or other type of attribute maps are stratigraphic or structural, such as faults, is to look slightly above and slightly below. The faults will stay in about the same place. The stratigraphic features will come and go quickly as you go a little bit above and a little bit below the particular horizon that you're interested in. There are several or two main types of applications for seismic attributes. One is a qualitative application. I'll show some examples of this. One qualitative is data quality, trying to figure out how good is the imaging, or do I have minor or major seismic artifacts. Another qualitative application is seismic facies, trying to figure out depositional environments, and I have an example of that coming up. The other type of application is a quantitative application, and that's where you use attributes in an equation that the user has to derive that relates one or more attributes to a physical rock property or a fluid property. And so we might use one or more attributes to try to predict reservoir thickness or lithology or porosity, which is what I showed on the title slide, or maybe the type of fluid filling a reservoir. So for qualitative applications, here is an example. This is RMS, root mean square amplitude. It's a 200 millisecond window. It starts at 40 milliseconds below the water bottom. So the first step was to map the water bottom, and then to define a window that starts at the 40 milliseconds below the water bottom to 240 milliseconds below the water bottom. And as I look at the amplitude map for this really shallow interval, I can see something that doesn't look very geologic. It's these east-west stripes or lineations. These are acquisition artifacts, and most 3D surveys will have these in the shallow section. They tend to heal with depth, which is what I'll show you on the next slide. So even if I didn't know which way the boat sailed, the inline direction, I could look at a map like this, an attribute map, see the east-west stripes, and that would tell me right away that the boat was sailing west to east, turned around, went east to west. It was not shot north-south, south-north. This is the same data set. Now I have a window that starts at 1,000 milliseconds and goes down to 1,200 milliseconds. So again, it's a 200 millisecond thick window. I'm looking at root mean squared amplitude. I know from the previous slide that the inline striping should go east-west. And now I see very subtle stripes east-west, but I also see features such as this blob that's in the lighter colors of maybe a lighter, lower root mean square amplitude. The green would be intermediate and the blue would be the higher root mean square amplitudes. And so this is telling me something about the stratigraphic bodies that are within this 200 millisecond window. Another qualitative application is to do seismic facies or seismic texture. In this case, and this is an example that Passementir and Kola published in 2003, Henry is known throughout the industry for seismic geomorphology. This is one of his earlier examples. What you do in this case is you tell the software what window you want to analyze and how many different classes you want the computer to come up with. So it will look at the waveform within that window throughout the survey. It will look for the more common types of responses, and it will classify 10, if I said 10 classes, it would classify 10 different shapes. And then the color indicates whether it's at each trace it's closest to class 1 or class 2 or class 3 or class 4 response. So we haven't applied any quantitative numbers. We haven't quantified the lithology or feet of thickness or fluid content or anything. But you can see that something is meandering through this slice, and so that turns out to be interpreted to be a fluvial meandering system. And I believe for this data set, there are some wells that can verify that, yes, indeed, that is a major channel complex. So you can look at images like this and start to see, in some cases, geomorphic patterns that help you interpret what type of environment of deposition. And then you can start talking about where the point bars would be and where the thalweg of the channel would be, where the overbank deposits would be, and infer from that something about the environment of deposition and the different lithophases or rock types. If we want to do a quantitative application, we have some requirements. We need appropriate data processing. We don't want to do something in data processing that would destroy the relationship between reflection coefficients and the seismic amplitude. So usually what we would ask our processors, has the processing been somewhat of a controlled amplitude and a controlled phase set of processing. We'd have to do a seismic data quality reconnaissance. If the data quality is poor, then doing some of these different types of quantitative analyses would not be trustworthy. We would look, if we have wells, at how well our well seismic ties are turning out. If we can't use well data and understand the response for our zone of interest, then it becomes questionable whether or not we can use seismic attributes to make geologic predictions. And because we are trying to be quantitative, we're trying to predict a rock or a fluid property, then we need some well control so we can do some calibration. And one of the things that we can do, and I'll illustrate this in some slides that are coming up, we may have a couple of wells, but then we can tweak the well data. Let's say we have a well with 10 feet of pay. We could say, well, what if that pay thickness was 50 feet? How would the seismic response differ? Or what if there was no sand, no pay within an interval? What sort of seismic response would that be? So we can use seismic modeling to generate some other conditions that would be within the range of possibilities. Oops. So I'll talk about an example where we used quantitative applications. It's onshore Alabama, and the intervals of interest is called the Smackover carbonates. We have the Haynesville clastics above it, then we have the carbonates, the Smackover, and then they sit on top of the Norphlet. In some wells, we have a porous zone at the top of the Smackover. In other wells, it's tight at the top of the Smackover. And if it's tight, it's higher impedance. If it's porous, then the impedance near the top of the Smackover is reduced. So here's a representative inline, and this particular display peak is in the hotter colors, the reds, orange, yellows. The troughs are in the shades of gray to black. And this dotted white line is the horizon that was mapped to correspond to the top of the Smackover. So on the right side, we have a well, and this is the well where the top of the Smackover was tight, no porosity. On the left, we have a well in this position. We see reduced impedance at the top of the Smackover, and you can see this trough has a different shape. It's a, from zero, it's a small excursion to the left and then a large excursion to the left. We compare that to where it's tight. It's a big excursion to the left, an intervening secondary maxima, and then another big excursion to the left. And so the amplitude response and the shape response, and if I go from zero crossing to zero crossing, the time thickness of the trough here is shorter than the time thickness is here. And so by looking at these two wells and how that trough changes from a porous location to a non-porous location makes me start to think maybe I can use some seismic attributes to quantify how much porosity I have within the upper Smackover. Here is an example from the same data set or data area. The actual well had 10 feet of a porous upper Smackover, and this is the modeled seismic response, and so this is the trough corresponding to the top of the Smackover. I can do a what if, I can do some editing, and instead of 10 feet, I can make the porous zone 16 feet and model what response that would give. And you can see that the trough has changed in its shape. And then I could also say, well, what if it was thinner? What would happen if instead of 10 feet of porous zone, I only have 3 feet of porosity? And you can see that, again, the shape of that trough is different. In this case, with just 3 feet, we actually get an intervening peak that we don't see when it's 10 feet, and we certainly don't see when it's 16 feet. So by doing seismic modeling, I can supplement my actual wells with what we commonly call pseudo wells, and we can measure how different seismic responses would change as different rock or fluid properties change. So for this particular onshore Alabama case, we had 8 calibration wells, and we developed an equation that used 4 different attributes, some related to amplitude, some related to the time thickness of the trough, some related to the symmetry or asymmetry. We came up with an equation, and this is a plot of the actual Smackover porosity versus what our equation based on the 4 attributes predicted. A perfect fit would be the black line, and you can see that the 8 points are close to that line, and the dashed blue lines is a 95% confidence interval. So it looks like I'm not doing too bad in making the prediction. If it was actually 4, I might predict it was about maybe 2.8 to 3.8. So I'm at least in the ballpark. And that's what was used to generate the map that I showed on the first slide. So instead of seismic attributes, now I have an equation that is predicting porosity. I have values for where the wells are shown, and all the places where there are no wells, this is what the seismic attributes would suggest. So there is production in the south and southeast. There's no production up here, but in this case, it looks like we might be at about 12% porosity. And so maybe this is onshore US, so the drilling costs are not too high. There's a lot of infrastructure, and we have a lot of energy-hungry people living in the US. And so it might be worthwhile to put in a exploration well, or you might call it a near field wildcat well, in this location, maybe in this location. There are some artifacts associated with the edge of the survey, and so we can calculate where we don't think our equation may be appropriate, and that's what the grayed out portion of the map is. And then if we are not working exploration, but we're working production, and we're interested in this particular feature where we have good carbonate porosity, we have a well, I believe the surface location is here, and this is where it hits the Smackover. We can start to consider how we might drill some extra wells in here to enhance recovery, and maybe use some wells as injectors to flush out even more oil from this particular discovered field. So in summary, seismic attributes, they describe the shape or other characteristics of a seismic trace over a specific interval or at specific two-way travel times. Seismic attributes are important because they enable interpreters to extract more information from the seismic data. Attributes can be derived from a single trace by a comparison of multiple traces or from interpreted seismic horizons. Three common types of attributes are single trace attributes. Three common types of single trace attributes. One is loop. You're looking at an individual trough or an individual peak where the horizon is picked. It could be an interval attribute. It could be from the top of the reservoir horizon to the base of the reservoir horizon. It could be, as I showed it with the artifacts, it could be 20 milliseconds, or was it 40 milliseconds, below the water bottom to 240 milliseconds below. Or it could be sample-based. This is where we look at some instantaneous attributes and we generate new volumes. If you listened to or viewed the lecture on structural mapping, I talked about coherency volumes. That would be an example of a sample-based type of attribute. Attributes are used for qualitative analysis, such as data quality or seismic facies or seismic texture analysis. And they can also be used quantitatively, predicting things as net feet of sand, porosity, fluid content, where might the contact between a gas sand and a water sand lie, as an example. There's an exercise associated with this unit, and we look at an area again in Australia. Here I have some seismic models, and so this response here, which is what I'll call my wiggle, it is zero phase data that has been rotated by -90 degrees. And we do that so that the boundary becomes a zero crossing. And then in this case, this loop above the boundary tells me something of the properties of the seal, and the trough below the boundary tells me something of the properties of the reservoir. And so in this particular area, if I have good quality seal and a good quality reservoir, I'll get a strong peak above my interpreted horizon, and I'll get a strong trough below it. If the seal is poor and the reservoir is good, I'll get a low to moderate amplitude peak with a strong trough. If the seal is good, but the reservoir is less quality, then again, I'll get a strong peak telling me I have a good seal. I'll get a moderate to low amplitude trough telling me that the reservoir quality is not so good. And if I have a poor seal and a poor reservoir, I'll get a moderate peak and a moderate trough. So based on seismic modeling, I've made the observation that if I analyze the peak on top of my interpreted horizon, which is where the dashed red line would be, if I get a really positive number, then that's a sign that I have a good quality seal. If I look at the trough below that horizon, I get a really big negative number, that tells me I have a good reservoir. And so this map is in the exercise material. It shows me the peak that's above the orange horizon. And so I want to see a strong response, so I'd be interested in things that are green and yellow and maybe orange. And then the trough below it, I want strong amplitudes. And so the sign has been flipped around. The white and the blue are weak amplitudes, so low negative numbers. The yellows and oranges are higher negative numbers. And so I'd like the green and the yellow, and I don't think there is orange and red on this. And so I can look at these two and find where do I have the superposition of good seal sitting on top of good reservoir. And so that's an exercise that you could do if you find this type of analysis of interest. So that finishes my prepared remarks. As I said, there certainly is a whole lot more that could be said and done, applications that are used, but given my time frame, that's kind of a quick overview of the use of attributes and why it generates a lot of excitement. So I'll put up my agenda, dates, and I'll turn the discussion back over to Dr. Sumi and see if there are some questions that we have from the audience.
Great, thank you, Fred. As we get questions rolling in, I'll give you guys a second to kind of enter in your questions and shoot them onward. Yeah, as Fred mentioned, we have some upcoming webinars for the next sort of like week and a half to 2 week time frame. And then we're going to take a pretty significant break in the middle of October. And then we'll be back for the last series of lectures starting October 24th. So we look forward to that. Just take another second to see if there's any questions coming through. Haven't had anything yet. Okay, well, it doesn't seem like we have any questions that are coming through right now. So I guess with that, we'll end our webinar and we will see you this upcoming Thursday at 2 p.m. Eastern time, where the webinar will be on reservoir quality. So see all of you then.
Thank you all for your attendance, and thank you, Dr. Sumi, for coordinating it once again.
All right, thanks. All right, bye everyone.
Everyone have a great afternoon.
All right, bye.
Bye-bye.